Okay, I'm sorry about this one. Actually, I was wrong when I think about this calculation. Okay, let me explain again. This homogeneous transformation is based on A frame, and we are thinking about the F frame. So in case of here, okay, based on A frame, we are thinking about the YF frame. The YF frame is equal to minus Z direction. So it becomes -1 here. So this column and row position was changed, was wrong. So we should think about XF, FYF, and ZF based on XA, YA, ZA. So when we think XF, it is same direction with XA, so 1, 0, 0. And when we think about FYF, it having minus Z direction, so it becomes 0, 0, -1. And we think about this ZF, and it is same direction with YA direction, so 0, 1, 0. It becomes 0, 1, 0. So it should be, it is correct. So this one is correct. So the result is something like this. Okay. Yeah, this one is about the example 3.28. Okay, let's think other cases. Okay, we done 3.28, and we learned about wrench, and also be careful about this one. The transpose is not going to here. We should use the transpose in here. And this one is correct form of the wrench. Okay. That's it. The wrench was the final contents of our class, the chapter 3, actually chapter 3. So let us go through from the first of the chapter 3. Okay. In chapter 3, we learned about rigid body motion. Okay. We learned about spatial velocity, that is twist. This twist concept is most important one in our class. So, and why it is changed? Okay. So we learned about fixed frame and space frame, and also these two concepts is same one, and we learned about body frame. So the base coordinate is important thing, and when we think some position, we should know about the basis frame and the target frame. So, and also we are using the right-handed rules. So it is very important to follow the right-hand rule. And let's think about the example. Yeah, we learned about rotation matrix and also the translation of this one. And when we learn about this one, we also learned about the absolute transformation and relative transformation. And also we learned of the screw motion. And the concept of screw was normalized twist, and screw motion itself is about when we describe some rigid body motion, we can describe it by using screw motion. And so in the screw motion, there is rotational velocity, and also there is a rotation pitch, and also there is a translational velocity. Before we continue, it is better to understand about this one. This concept, actually I didn't explain before, but it is very helpful to understand the concept of screw motion. Actually, the left side one is this kind of elliptical rigid body was located in here. Firstly, it rotated like this. So the C coordinate go to this position. And in this example, we represented P. Actually, this P is rotation matrix. So rotating matrix, by using P matrix, rotation matrix, the rigid body rotated like this. And then it transformed using a translation using P vector. So firstly, rotate like this. So it becomes here, and it translates like this. So these two motion can be presented by PR plus P, small p. So this P is rotating matrix, and the small p is translation. Because this one is planar case, we simply express like this. But this kind of motion can be simply expressed using this screw motion. Screw motion means there is screw axis in this point, and when we rotate this rigid body based on this screw axis about 90 degrees, this rigid body becomes this one. So D position, D coordinate move D prime, and C coordinate move to C prime, very simply. So let's think about this one. Actually, this transformation was done rotation first and then translation. So it is a little bit complex. But in the case of this one, this movement just parameterized by three value. First one is rotation degree, beta, and second two things is the position of screw axis. The screw coordinate is located on 0.2 here. And using this screw motion, screw is some kind of screw. So rotate like here, 90 degree. It becomes this rigid body, move to this one. So if we know the 90 degree and 0, 2, then we can represent this rigid body motion. And also, about these contents is about the concept of twist. Actually, this one was the position of screw coordinate. But in case of twist, we use angular velocity and linear velocity. So when there is angular velocity here, and if we assume this angular velocity is 1 radian per second, the momentum here from the screw coordinate origin to the S-frame, the momentum is 2. So the velocity in S-frame is in the X direction is 2 and Y direction becomes 0. So Vx equal 2 and Vy equal 0. So this meaning is the here. The omega is 1 and Vx Vy equal to 0. So this one is already we learned about the screw axis. So this motion and this motion is same thing but different expression. So, and also if we calculate the S multiplying theta, then it becomes like this. And this one is exponential coordinate. So by using this information, we can get the homogeneous transformation matrix. And actually, this concept came from when the omega equals 0. So actually, it becomes the theta dot and theta dot equals theta. It means unit time. So because we just assume omega equal 1, we can using this kind of expression. So in our class material, we also assume this kind of things. So I review about this one, and let's continue to the rotation matrix. So special orthogonal group SO3, large SO3, we learned about this. And in the rotation matrix, transpose and inverse is equal. And the rotation matrix can be parameterized by 3 values. So that is the angular velocity vector. So using this vector, we can represent the rotation matrix. So in the case of the head symbol, it represents the unit vector. So because the size of a unit vector is equal 1, actually there is 2 independent value in this angular velocity vector, and one more independent value is theta. So it becomes 3 value. So rotation in the rotation matrix, the independent value is always 3. And also we learned about the angular velocity, and in here the skew symmetric 3 by 3 skew symmetric matrix was important. Actually, skew symmetric matrix is small SO3. So we learned about large SO3, small SO3. And skew symmetric matrix is basically the cross product. So we learned about the skew symmetric matrix of omega s is equal to R dot R inverse, and R inverse R dot is body angular velocity skew symmetric matrix. And we learned about exponential coordinate representation. So using the unit angular velocity multiplying theta, we can get rotation matrix. So in here, we learned about this one. So skew symmetric matrix of angular velocity, unit angular velocity vector multiplying theta. This one is small SO3, and this small SO3 can be transformed to large SO3 using exponential. So this one was Rodriguez formula. And by using logarithm, we can transform large SO3 to small SO3. And in case of homogeneous transformation, we can also calculate the exponential coordinate. In case of homogeneous transformation, there is pre-multiplication, and post-multiplication, and there is relative transformation and absolute transformation. Okay. Yeah, and then we learned about twist. Twist is very important concept. Twist is equal to spatial velocity. So we can describe the rotational velocity and angular velocity in the same matrix. So in here we learned about large SE3. So large SE3 is homogeneous transformation matrix, and the small SE3 is this one. Yeah. The bracket of this twist becomes 4x4 SE3 form. So we call this one 6-vector form, and this one we call this one is SE3 form. So this one is 6x1, this one is 4x4 matrix. And okay, we learned about the other joint representation. So between two homogeneous transformation matrix, there is adjoint relationship. So here, between this twist B and twist S can be related by adjoint TSB. So this one is about the adjoint. Okay, let's solve example 3.23. In this example, we showed top view of a car with a single steering front wheel. So this one is front wheel and steering wheel. The jet B is axis of the body frame B, body frame of B, and go into the page. So this one is X, this one is Y. We using right hand like this, then it go into the screen, and there is Z axis and ZS axis of the fixed frame is out of the page. Yeah, this one out of the page and go into the page. The angle of the front wheel of the car causes the car's motion to pure angular velocity. Yeah, this one is front angle, and by making the line perpendicular to the wheel, it goes here, and the rear wheel goes here, and it meet on this point. So the angle of the front wheel of the car causes the car's motion to pure angular velocity 2 radian per second over about an axis out of the page at the point R. And here there is omega here, and the size of the omega is 2 radian per second, and rotate like this. Inspecting the figure, we can write R as minus 2 minus 1 0. So 2 here along the x-axis and y-axis minus 1. So the point of R based on S frame is 2 minus 1 0. And based on the P frame along XB is go 2 point, and in the y direction, in the minus y direction, minus 1.4. And omega S is 0, 0, 2, and omega B is 0, 0, minus 2, because the Z direction came out over here, and Z direction in B go into the page. So we know about this information, and also we know about the TSB, because S frame here and B frame here, the rotation matrix based on the S frame, based on X frame. Okay, XB frame is minus XS direction, so minus 1, 0, 0. And Y direction equal to YS axis 0, 1, 0. And Z direction is minus 0, 0, minus 1. And the position of this one is 1, 2, 3, 4. And this one is 1, and this one is 1.4. So it becomes 0.4. So we know the TSB. Then what is the what is the problem? We only know omega s and omega b. So in this problem, we can calculate Vs, Vb. So when we calculate Vs, R S cross product omega s. When we calculate Vb, Rb cross omega b. So we can get this one. In that case, the Vs become like this and Vb become like this. So in this example, they want to confirm this result by calculating this one. Okay, let's do this one. Example 3.2 to 3. Okay, firstly, we have TSB. TSB is -1, 0, 0, 4, 0, 1, 0, 0.4. And 0, 0, -1, 0. Okay. This is TSB. Okay, then if we have do twist B equal 0, 0, -2, 2.8, 4, 0. Okay. Then let's make MR adjoint TSB multiplying VB. Then it becomes 0, 0, 2, -2, 4, -4, 0. Yeah, it's exactly same. So this relationship is valid. So we can recognize this one is screw motion. So this is kind of screw axis, and this screw motion, using this screw motion, this rigid body go this way. So when we describe the motion of this one, we can use the screw motion. Simply, you can use screw motion. Okay. So this one came out before we learn about screw interpretation of twist. So we learned about this one. Actually, this part is a little bit confusing because we are using same symbol in here and also in here. But we should know about the screw is normalized twist, the concept of normalized twist. So in here we learned about the exponential coordinate of homogeneous transformation using screw axis multiplying theta. So this one go transformed to T, homogeneous transformation T. And the calculation of position vector can be calculated by G theta multiplying V. So this V is this one. And so in this example, this omega is this one, not this one. So you should be careful. In here, this one is this one, and this V is this one. Okay. And let's do this one. Example 3.26. Okay, this one is one of the example of screw motion. In this example, rigid body motion is confined to the plane case. So initial frame, B frame, and final frame, C. And screw motion is here. So omega 3 is 1 radian per second, and function Q is here, screw coordinate, and it moves about theta. In that case, the velocity in S frame V equal 3.37 minus 3.37. Okay. Because this velocity is equal to the angular velocity multiplying the distance. So because the Q position is 3.33, it becomes this one. Yeah. If we draw the line from here to here, we can make this velocity in here. Okay. So in the case, the TSB is something like this, and TSC is something like this. This is known parameter. And because the motion curve occurs in the plane, the corresponding screw has axis in the has zero pitch. Yeah, because this is a plane motion, so pitch is zero. And screw axis S is omega V expressed in S plane, therefore has the form omega equal 0, 0, omega 3, and V1, V2, 0. Yeah, okay. We seek screw motion, then displays the plane at TSB to TSC. TSB to TSC. So we in this example, we want to find the screw motion from TSB to TSC. That is TSC equal TSB sum. Yeah. So the meaning of this one, okay. So yeah, there is this. Yeah. So in here, some homogeneous transformation from S to B, TSB, and there is some absolute transformation based on screw motion. So we define some screw motion here, and we pre-multiply this one before TSB. Then it becomes TSC. So we want to find this one. What is this one? So in the case, we can calculate TSC, TSB inverse exponential as etc. So this calculation Okay, let's do this one first. Okay, let's make TSB first. TSB 1 pi dot cosine 30 degree. Something like this. Okay, helpful NP cosine. Okay. Okay, let's search pi cosine degree. Where was that? Pi cosine degree. Okay. Should we use this conversion? As I know, there is some as I know, there is some option to input the degree value. Basically it okay. Yeah. In here, we should input the radian value in the np.sine function. So basically, we should input the radian value. But I want to input the degree value. How can it? Okay, just multiplying this one. np.pi multiplying this, and this one is minus sine plus sine 1, 2, 1. Okay. cos SC. This one is 60 degree. 60, 60, 60, 2, 1. Okay. Okay, then we should calculate TSC multiplying TSB inverse. In the case, we can use MR transinverse inverse. You can using tab key TSB key. Okay. Yeah. This one is equal to the exponential coordinate of screw S. And if the omega is here and V is here, then we can get the screw. What is the SC3 form of screw? So if we take the matrix logarithm to here, we can get this one. So let's take a matrix logarithm. So matrix logarithm is this one, matrix log 6. Help MR dot matrix log 6. Yeah, input is T. And make it T here. And then like this. Yeah, we can simply get the omega here and V here. So this one is SC3 matrix. But in case of screw, we should get the normalized twist. So we should get the normalized value. In that case, we can use the axis angle 6. So using this function, we can decouple the screw axis and the size. So 6 vector form using 6 vector form. Yeah. So actually, we should use two functions. So SC3. So yeah, SC3 to correct. Yeah. Firstly, we should transform SC3 matrix to vector form. And we can get the 6 vector form. This one is 6 vector, twist 6 vector. And using angle axis 6, we can get screw and the theta. Okay, this one is omega 110. So this one is normalized, and this one is V. So 3.37 minus 3.37, and this one is angle value. Actually, if we calculate this one, is same one. So this one is right. So this S means let's this analyze this value S value. So this one is 1 and V is 3.37 minus 3.7 and 30 degree. So this theta means 30 degree. Theta equals 30 degree. So because TSB and using some screw rotation, it becomes SC, TSC. And this screw axis is same with this motion. And in here, we found this theta value using this kind of calculation. So actually, we found the 30 degree. So yeah, that's it. So this is the meaning of screw motion. So in this example, it shows the meaning of the screw motion very well. Okay, that's it. This is a example important example on chapter 3. Yeah, I will upload this file on the LMS system. You can use this file, and as a result, we finished our chapter 3. So in the case of exercise, you should practice yourself. You should practice yourself, and the more important thing, actually, this is we have middle exam, middle examination, midterm examination. Okay. Actually, this week 7 week, and this is 8 week, and this one is 9 week. And I will announce when we take an exam. Actually, this is our class time, official class time, Thursday, 1 p.m. At this time, we will have midterm exam. I thinking we will take a midterm exam in the offline because it is a little bit difficult to take an exam in the online. We will have offline exam, and basically we will have the examination on the 7 week and 8 week. This day or this day. So I will make a vote how to choose the midterm examination. So I will make the vote in KakaoTalk. You should check, you should choose one of them. And the midterm exam, I will give the midterm exam problem will be came out from the 3.8 exercise. It means there is exercise problem 1, 2, 3, 4, 1. There is 49 problem, and among these problem exercise, I'll make a midterm examination. So I hope you to prepare very well, and I will make a announcement in the LMS system. Okay, that's it. Today's class is over. Thank you.